Have you ever noticed that tanker trucks, the massive vehicles that transport fuel or other liquids, are usually rounded instead of square? There's a reason for that, and it's not just a random design choice. Every curve, every dimension, is carefully engineered to make sure these trucks are both safe and efficient on the road. Even though it might seem like a simple metal cylinder on wheels, a lot of science goes into keeping these trucks from tipping over or spilling their cargo, especially when they're partially loaded. Let's start with the basics. A big challenge with tanker trucks is something called sloshing. That's when the liquid inside the tank moves around while the truck is turning, accelerating, or braking. If the liquid moves too much, it can actually destabilize the truck and cause accidents. In fact, a large number of tanker truck accidents happen while turning, primarily because the fuel or liquid inside the tank splashes and shifts unpredictably. So engineers have to think carefully about how to design the tank and its internal components to minimize this problem. In countries like Ethiopia, all fuel and crude oil are imported, which makes transportation expensive. So it's not just a safety issue. Efficiency and cost-effectiveness are also important. Heavy-duty trucks carry these fuels, and their design needs to account for how liquids behave inside tanks under all sorts of conditions. One key element in controlling liquid movement is the baffle system. Baffles are like internal walls or dividers inside the tank that help break up the liquid motion. Traditional baffle designs work okay when the truck is accelerating or braking, but they aren't as effective during turns, which is often when sloshing becomes a real danger. Back in the late 1970s, researchers started looking into what happens when liquid sloshes around in partially filled road containers. One study in particular focused on how different baffle designs could reduce lateral sloshing. That's the side-to-side movement of the liquid. They tested a bunch of setups in modified oval-shaped tanks filled to about 50% and 80%, which are pretty typical for tanker trucks. To get a clear picture, engineers first modeled the trucks and baffle systems in CATIA 5, then ran simulations using CFD software in ANSYS Fluent 2021 R2. On top of that, they used ANSYS LS Darna for dynamic analysis to see how the trucks would handle lateral forces in real-world conditions. The study included 8 different baffle systems, such as the existing transverse baffles, TB, bottom-mounted longitudinal baffles, BMLB, upper-mounted longitudinal baffles, UMLB, curved longitudinal baffles, CLB, and multi-hole longitudinal baffles with different arrangements, like 2 HLB, 2 VHLB, 4 HLB, and 4 VHLB. After running the simulations, it was clear that the transverse baffles weren't very effective at controlling lateral sloshing during turns. But the baffle system that performed the best was the transverse baffles combined with bottom-mounted longitudinal baffles, with 4 holes whose positions varied. For VHLB, it turns out that having multiple small holes strategically placed helps dissipate the energy of the moving fluid and significantly reduces the forces acting on the truck. To give you some numbers, using the 4 VHLB design at 50% fill reduced maximum lateral force by almost 48% and roll moment by nearly 59%. At 80% fill, the reductions were about 58% for lateral force and 22.5% for roll moment. So this kind of baffle design doesn't just make the truck safer, it literally stabilizes it during sharp turns, which is crucial for avoiding rollover accidents. Now let's talk about the tank itself. The modified oval tank is defined by 5 main parameters: the upper and lower radius, the side walls, the blend arcs of the radius, overall height, and width. Essentially, the tank is constructed from 8 arcs that are mathematically coordinated to give the oval shape. The design ensures structural stability while allowing the liquid inside to flow in a controlled way, especially with baffles breaking up the motion. The existing design includes 4 transverse baffles with an orifice and a bulkhead dividing the tank into sections. The transverse baffles are equally spaced, and the bulkhead divides the tank into equal 6-meter segments. These baffles and partitions work okay for some situations, but aren't ideal for cornering because they don't fully manage the lateral sloshing of liquid. The study tested new baffle designs arranged longitudinally along the center of the tank. These baffles stretch across the tank's length, 12 meters, and are about 75% of the tank's height. This partial height keeps the truck from becoming too heavy while still effectively controlling the liquid movement. There were also two ways of mounting these baffles, bottom-mounted and upper-mounted. And within that, there were straight and curved designs, with curved baffles slanted at 9 degrees from the tank center. Another important factor was the number and arrangement of holes in the baffles. Some designs had a single hole per partition, while others had 2 or 4. The position of these holes also varied. They could be in-line or staggered. The study found that increasing the number of small holes in staggered arrangements helped reduce sloshing the most because it lets the fluid energy dissipate gradually, rather than hitting a solid wall and bouncing back. Before running simulations, engineers created a mesh of the tank in a meshing tool. They tested different mesh sizes to make sure the results were accurate and not dependent on the mesh. This grid independence test is crucial because using a mesh that's too coarse could give inaccurate results, and using one that's too fine would take too long to compute. The study found that a 40mm mesh offered the best balance between accuracy and computation time. Once the mesh was ready, the fluid was modeled using the volume of fluids VOF approach in ANSYS Fluent. This method tracks the free surface of the liquid rather than just individual particles, which is perfect for studying sloshing. The primary phase in the model was air, and the secondary phase was diesel, with densities and viscosities set accordingly. The standard K-epsilon turbulence model was used to account for fluid turbulence, which affects how the liquid moves around inside the tank. Boundary conditions were applied to make the simulations realistic. For example, the tank was assumed to accelerate at 2.65 meters per second, squared along a curved path with a 30.48 meter radius at a speed of 9 meters per second. This mimics how a truck would behave during a turn on a real road. Operating density and pressures were also specified, and transient analysis was used to track how the liquid moves over time. The tanker truck itself was modeled in 3D using CATIA Viv 5. For simplicity and accuracy, only critical components like the tanker body, bulkhead, baffles, and chassis were included in the model. Non-critical components like hoses, clamps, and ladders were removed because they don't impact stability, but would make the model unnecessarily complex. The CFD results were then imported into LSDYNA to run dynamic analysis and see how the truck would actually respond to lateral forces. The simulations showed some interesting results. At both 50% and 80% fill levels, the volume fraction of diesel indicated how much of the tank was filled with liquid versus air. The red areas on the plots showed diesel and blue represented air. When the truck was in motion, the transverse baffles didn't do much to prevent lateral sloshing, and the liquid would hit the side walls, increasing the cornering moment and the risk of rollover. On the other hand, the 4-hole longitudinal baffles with staggered hole positions kept the diesel moving more calmly, significantly reducing lateral forces and improving stability. Pressure contour plots reinforced these findings. At 50% fill, the liquid had more room to move, so the pressure along the side walls could spike. At 80% fill, the liquid motion was less dramatic, but the total mass meant forces were still significant. The staggered multi-hole longitudinal baffle design helps spread out the pressure, preventing dangerous spikes and enhancing rollover resistance. When comparing different baffle systems in tanker trucks, the 4-hole staggered longitudinal baffle performed the best in reducing lateral forces, while curved baffles offered some help but could cause sudden spikes that might compromise stability. Vertical forces were less affected, particularly at higher fill levels, but roll moments were another critical factor. Again, the 4-hole staggered baffle showed significant reductions, keeping trucks stable during turns. To ensure accuracy, the CFD model was validated against experimental data in previous studies on cylindrical tanks, showing close agreement. Further validation with gasoline in a partially filled rectangular tank confirmed that baffles effectively reduce liquid movement over time. The study made it clear that not all baffle designs are equally effective. Traditional transverse baffles do little to prevent lateral sloshing and can even increase rollover risk, especially at partial fills like 50%. Although higher fill levels reduce sloshing slightly, the forces remain significant due to the mass of fuel. The multi-hole staggered longitudinal baffle proves superior because it separates fuel mass and dissipates energy efficiently, reducing lateral forces and roll moments by up to 58%. Overall, tanker truck design involves meticulous engineering where every curve, hole, and placement is calculated to maximize stability, safety, and efficiency, showing that the science behind these vehicles is as crucial as their size and power. And that's that for today's video. Thanks for watching, and we will see you in the next one.